Good morning, everybody. Today is 20th November 2020, and the day is Friday. Right now, I am with the 11th Cambridge class. The subject we are studying is Physics 5054, and this is the O-3 class, and we have set out the task for today. We want to do the MCQs related with the radioactivity. So we will try our best to do this. Okay, so let's start. You can see on your screen, this is radioactivity. This worksheet I have taken from a website. The name of the website is savemyexam.co.uk. So this worksheet is coming from that. Okay, on your screen we have the first question coming from on your screen is which type of radiation consists of electrons? The radiation is of three kinds: alpha, beta, gamma. The radiation is of three kinds: alpha, beta, gamma. And the beta particles, they are negatively charged. So the radiation, which you can say is like electrons, is beta part. So the choice is B. The choice is B. Do you understand?
Yes, sir.
Okay. The next one on your screen, a sample of radioactive isotopes produces a count rate of 1000 pounds per minute. The half-life of the isotope is 1 day. What are the count rate of the sample 2 days ago? Okay. So,
B.
you know the answer? Let me take out the
I have
paint.
calculated.
Let me take out the paint and then we will. Okay. So the count rate is. Okay. So the count rate is how much? 1000. And their question is how much it was uh, 2 days ago. Okay. So today is this. Okay. So one half life before what it was, and the actual question is two half lives before how much it was. So whenever half life passes by, you know, the amount becomes half. So if 1 day before, in 1 day it has become half. So whatever double it, so that is the amount it was 1 day before. It's a reverse percentage kind of question. So this is the present radioactive count. And 1 day before, I mean one half life before, it was 2000. And before that 1 day, if you go back 1 day further, it was double of 2000. So it was supposed to be how much? 4000. During each half life, the thing becomes half. Okay. So if this is the present value, if this is the present value, this is the present value. So what was the value 2 days ago? So this is the present value. Okay. This 1000 is the present value. So what was the count rate 2 days ago? And because the half life is 1 day, so 1 day before it was 2000, and further 1 day before it, that day, that was 4000. Do you understand?
Yes, sir.
So the answer should be 4000. Okay, so the D looks no.
It's
Sorry,
10,000.
it was 40,000. Okay, I wrote there 1000. It was 10,000. So 1 day before it was 20,000, and another 1 day before it was 40,000. So D is the choice. Do you understand?
Yes, sir.
Okay. So the next question is question number 3 on your screen. Which nucleus is produced when americium emits an alpha particle? When an alpha particle is given out, the when an alpha particle is given out, the mass number will reduce. Let me show you here. The mass number should be reduced by 4. When the alpha particle is given out, the new mass number should be 4 less. So it was 241. So 241, it should reduce by 4. Let me 241 minus 4. So what will be the answer? 241 minus, I think, 337. And the proton number, that is reduced by 2. So previously it was 95. It should be reduced by 2. And the final answer will be 93. So the right option is that when the mass number is 337 and the proton number is 93. So A looks the right answer. Do you understand?
Yes, sir.
Whenever an alpha particle is given out, the daughter nucleus, its mass number will be 4 less than the parent nucleus mass number, and its proton number will be 2 less than the proton number of the parent nucleus. Okay?
Yes, sir.
Next question. Which states the 3 types of radiations emitted by radioactive isotopes in order of their ionizing effect from highest to lowest? From highest to lowest, the highest ionizing power is alpha has the highest power, and then we have beta, and then we have gamma. So the arrangement should be alpha, beta, gamma. That is, the alpha has the strongest ionizing power. It has the highest ionizing power. Then the beta has ionizing power, and the lowest ionizing power, gamma's ionizing power, is lowest. From highest to lowest, we have to write. So it should be alpha, beta, gamma. So what's the choice?
A.
A is the right answer. Question number 5. Which statement about the half-life of radioactive isotope is correct? In the half-life, the original sample of the radioactive isotope decays, and only half of the original isotope, the half of the sample decays in that time. Half-life is the time it takes for the nucleon number of the isotope to half. No, half-life is the half the time it takes for the number of nuclei of isotope to decrease to 0. No, half-life is the time it takes for the number of nuclei of the isotope to decrease by half. That is the right definition. So D is the right answer. You see, mark this definition. Sometimes what happens, you have to write this definition in the theory paper. You see, it's very important. So this is the definition of the half-life, and sometimes it also comes in the theory paper. It might be of 2 marks definition in the theory paper. There you have to write this definition. Here CAIE has provided itself the definition of the half-life. Half-life is the time it takes for the number of nuclei of the isotope to decrease by half. Got it?
Yes, sir.
Okay. A factory continuously produces plastic sheets. A radioactive isotope and a detector are used to check the thickness of the sheets. What is the most suitable source to use? An alpha source with a half-life of a few minutes? No, alpha particles will not be able to pass through the plastic sheet. An alpha source with half-life of several years, alpha particles cannot pass through the plastic sheet. C is a beta source with a half-life of a few minutes. Beta is the suitable thing to check the thickness of the plastic sheets because the beta particles they can pass through the plastic sheet, but the half-life should be several years. So because when you have once installed the radioactive source in your machine, and then it should be good for a few years. If its half-life is a few minutes, you have to again and again replace the source. You have to buy the new one and put it there. So that's why the beta source is good and the half-life should be several years. So the best choice will be D choice. What do you say?
Yes, sir.
You understand?
Yes.
Source contains the radioactive material. Without the radioactive source present, a detector records a background count rate of 20 counts per minute. This source is replaced by a fixed position near the detector. Is placed in a fixed position near the detector. Initially, a count rate of 520 per minute is recorded. What count rate is recorded after a time of two half lives of the radioactive source? Okay, let me do this. Let me show you how it is done. Take out a new one. So the count rate is coming out to be 520. Subtract from it the background radiation. So actual samples reading is 500. 520 minus 500. You see, whatever the reading is coming, that reading includes the background radiation. So what I will do, first of all, I will subtract the background radiation from the reading of my detector. So the reading from the sample, the reading purely coming from the sample should be 500. So when the two half-lives have passed, you see the original reading is how much? 500. The original reading is how much? 500. So when one half-life would have passed and then the second half-life would have passed, this after one half-life, it will become half. So this thing will become how much? It will become, uh, sorry, this will become 250. If you have 500, it will become 250. When another half-life will pass, this 250 will further half and it will
125.
become 125. 125. Now the question is, what will be the reading shown on my detector? 125 will be coming out of that sample. 125 will be coming out of that detector. In this reading, this is the purely coming from the source. Sorry, I said detector. 125 reading will be coming out of that source after two half-life. Background will be still there. So add the background reading in it. So the final answer will be, the reading on the detector will be
145.
145. Do you understand this?
Yes, sir.
Okay. So the final answer, the reading on the detector will be 145. 145. So what is the choice? The choice
D.
will be It should be 145. E is the right answer. Do you understand?
Yes, sir.
Okay. On your screen, we have next question, and that question is a nucleus of uh, PO, polonium, I think. It's 21584, decays by emitting an alpha particle and the resulting nucleus then decays by emitting a beta particle. What is the nucleon number and the proton number of the final? So two decays are happening here. Okay?
Yes, sir.
Okay. So here you see, so let's say what happens with the nucleon number. Nucleon number. Okay. First, an alpha decay happened. Whenever an alpha decay happens, the nucleon number decreases by 4. The nucleon number decreases by 4. So the nucleon number will become equals to 211. You understand this? Then,
Yes, sir.
then what happened? The then a beta particle was emitted. When the beta particle is emitted, the nucleon number increases by 1. Sorry. When the sorry, when the beta particle is given out, there is no change in the nucleon number. So the final nucleon number should be 211. That is the story of the nucleon number. Then we have proton number. Proton proton number. You see, when the alpha particle is given out, the proton number decreases by 2. Okay, so it will become 82. And when an beta particle is given out, the proton number increases by 1. So the final answer should be 83. Okay, here two particles are given out, alpha particle and then a beta particle. For the nucleon number, you see, when the alpha particle is given out, the nucleon number decreases by 4. And when the beta particle is given out, there is no change in the nucleon number. So you can see our final answer will be 211 for the nucleon number. Proton number. When the alpha particle is given out, the proton number decreases by 2. And when the beta particle is given out, the proton number increases by 1. So our final proton number will be 83. So nucleon number should be 211 and the proton number should be 83. So the final answer, what will be the final answer?
B.
B. So B is the final answer. I hope you have understood. Okay? Do you
Yes.
understand? Okay. We are on the next question. The half-life of a radioactive isotope is 24 hours. A sample of isotope produces an initial count rate of 720 counts per second. How long does it take for the count rate to fall to 90 counts per second? Okay. So let me show you. Let me. Okay. So originally you have 720 count rate. When the one half life will pass, it will become half. So do you have calculator with you?
Yes, sir.
Okay. So take that your calculator also out and we will do the calculation. So what I will do, 720, after one half life, it will become half. So it will become 360. So when one half life passes, so it will become 360. When another half life will pass, it will further decrease.
180.
So 360 will be half, 180. So 360 will become 180, and it will further have, so 180 divided by 290. So you have to check how many half lives have passed. So one half life, two half life, three half life. So you can see that there are three half lives passed. So the total time taken will be equals to three half lives, and each half life is of 24 hours. So multiply 3 with 24, and you will get the answer. So multiply 3, 3 with 24, and you get
72.
72 hours. So the final answer will be 72 hours. Do you understand?
Yes, sir.
The final answer is 72 hours. By mistake, I have highlighted 192. The final answer is B, 72 hours. You understand?
Yes, sir.
Okay. So the next question is, which type of electromagnetic? Okay. Which type of electromagnetic radiation is produced during radioactive decay? Alpha particles, beta particles, gamma rays, X-rays. The, the particles which are given out during the radioactive decay are alpha particles, beta particles, and gamma rays. And if you remember, the gamma rays are part of electromagnetic spectrum. So gamma rays are electromagnetic radiation. So the answer will be C. You understand? You understand?
Yes, sir.
The gamma is the part of radioactive spectrum, electromagnetic spectrum, and so the gamma is the answer. In the Geiger Mazher experiment, a beam of alpha particles is fired at a very thin sheet of gold foil in a vacuum. What is deduced from this experiment? From this experiment, the Martian was able to tell that the atoms have a nucleus, and the nucleus is very small. The rest of the atom is empty. All the positive charge is concentrated inside the nucleus. So what he deduces from the experiment, nuclei are much smaller than the atom. So D is the right answer. Do you understand?
Yes, sir.
Okay. So let's move to the next question. The next question is, a radioactive isotope carbon 14 emits beta particle. A sample of this isotope is left for a period of time that is equal to its half-life, which two quantities decreases to half of their initial value during this time. If one half-life has passed, the decay rate will become half, and the number of atoms of the carbon 14 will also become half. So the right answer is the number of nuclei, the number of carbon 14 nuclei, they will become half after one half life. And the decay rate, which you will be observing on a detector like GMQ, that will also become half. So the C can be the answer. C is the right answer. Little bit tricky in the word. What do you say?
Yes, sir.
You understand?
Yes, sir.
Okay. Question number 13 is on your screen. Which row gives the range and electrical charge of an alpha particle? Alpha particle, they are like the nucleus of helium. They have positive charge on them. They have two protons, two neutrons. They are like the nucleus. They are not like helium. They are like nucleus of it. Okay. They have positive charge on them. And they're, because of their large size, their penetrating power in the air is very small. So they can penetrate only few centimeters in air. They have positive charge and they can only penetrate in the air few centimeters. So what do you think is the choice?
B.
D is the right choice. Alpha particles have the lowest penetrating power in the air. Which row states the nature and range of beta particles in air? The nature of the beta particles, they are electrons, and their penetrating power could be from 10 centimeter to 100 centimeter. So what is the choice?
D.
Oops. D is the choice, right? Three types of radiations emitted by unstable nuclei are electrons, helium nuclei, and electromagnetic radiation. What are these types of radiations? Electrons are beta, helium nuclei are alpha, electromagnetic radiation is gamma. So what is the choice? C. Electrons, beta are like electrons. Helium nuclei, alpha are like the nucleus of helium. And gamma rays, they are like electromagnetic radiation. So the right choice is C.
C.
C is the right choice. A sample of wood contains 9 expo 16 nuclei of carbon 14. The nuclei undergo radioactive decay with a half-life of 5,600 years. After how many carbon 14 nuclei remains in the sample after 16,800 years? So let's see how many half-lives have passed. One half-life is, let me show you what the calculator. One half-life, one half-life is 5,600 years. The total time passed by is 16,800. So divide the total time with the half-life, and so it will tell you how many half-lives have passed. So the total half-lives which have passed are 3. So now we will see how many are left, how many atoms are left, remain in the sample. Okay. So initially there were 9 expo 16. Let me go on this one. So the reading was 9 expo 16. Initial reading is 9 multiply 10 raised to power 6. Do you have a scientific calculator with you?
Yes,
Divided
sir.
with 2. So write on your calculator, can you write 9 expo 16? Can you write that?
Yes, sir.
Okay. Then divide it with 2. Get me the answer.
4.5
Yeah.
raised to power 16.
4.5 raised to power 16. Okay. So one half life passes by, so this much atoms will be left. Okay. Then divide again with 2. 4.5 expo 16 divided by 2.
2.25 raised to power 16.
2.25
Raised to power 16.
in expo 16. Yeah. So now two half-lives have passed. Okay. Again divided with 2. That will be our final answer. 2.25 x power 16 divided by 2.
1.125
1.125
x power 16.
125 expo. Let's see if this answer is valid there. So this will be my final answer. Okay, 6. It's very hard to write on the calculator on the thing. So 1.125. So 1.1 expo 16 is the right answer. So what's the choice here?
B.
Do you understand this?
Yes, sir.
Oh, people working with radioactive materials use a photographic film badge covered in paper. The badge is used to monitor the level of their exposure to radiation. Which radiation is detected? It is covered with paper, so it cannot be used to detect the alpha particles because the alpha particles cannot pass through the paper. So it cannot be used to detect the alpha particles. It can be used to detect the gamma and the beta. This badge, which is covered in a paper, can be only used to detect the gamma and the beta. It
C.
cannot be used to detect the beta particle. So C is the alpha particle. So C is the right choice. When a radioactive atom decays by alpha particle emission, its nucleus loses. Whenever the alpha particle is given out, the nucleus loses 2 protons. So 1 proton only? No. No, 1 proton and 1 electron? No. Two. The sorry, it loses 2 protons and 2 neutrons. Because whenever the alpha particle is given out, the mass number or the nucleon number decreases by 4. The mass number or the nucleon number decreases by 4. So whenever the alpha particle is given out, the right combination is the nucleus will give out 2 protons and 2 neutrons. In this way, the mass number will decrease by 4. So D is the right choice. What do you say?
Yes, sir.
Okay. A schoolkeeper keeps radioactive sources for use in the radioactivity experiment in a laboratory. The background radiation is measured at the start of an experiment. Which statement is correct? The background radiation is caused by the school's radioactive source in the laboratory? No. Background radiation is due to natural resources and it is always present around us. The background radiation is present when there are no radioactive sources in the laboratory. That is true. The background radiation is radiation that is not detected in radioactive experiment. No. The background radiation is the same in laboratories in different countries. That's not right. In different countries, in different locations, the background radiation value can be different. So the background radiation is present when there are no radioactive sources in the laboratory. That is true. Background radiation is always present around us, whether you have a sample or you don't have a sample.
Okay.
You understand?
Yes.
The count rate from a radioactive source falls from 4,000 counts per minute to 5,000 counts per minute in 72 minutes. What is the half-life? You see? So 4,000 to 5,000. So initially the reading was how much?
4,000.
4,000.
5.
So if one half life has passed, it will become how much?
2,000.
Yeah. If one half life will pass, it will become two
2,000.
2,000. It's very difficult to write. Okay. And another half life will pass, and it will become how much?
1,000.
1,000. And we are supposed to take it down to 5,000. So another half life will pass, and it will become
500.
500. Okay. So see how many half life has passed. Let's see. This is one half life. This is second half life. This is three half. So how many half lives have passed? Three. So the total time he said is 72, I think, minutes. And they are representing totally three half lives. So divide the 72 with three, and you will get the answer 20. So the half life of that thing is 20. You understand this? Do you understand?
Yes, sir.
Yeah? 24 minutes. So what's the choice? D. So the
D.
choice is D. What are the characteristics of an alpha particle? Alpha particle is like the nucleus of helium. It has two protons and it has two neutrons. It's the proton, the total mass number will be 4. Proton number will be 2. It has positive charge on it and it has very strong ionizing effect. It's
C.
positively strong. So C is the choice. So the C is the right choice. This is the right choice. C is the right choice. Alpha particles pass through an electric field or a magnetic field. How is the path of the particles affected by these fields? Alpha particles are positively charged. So when they will pass through the electric field, they will bend towards the negative. So they will be deflected. Alpha particles are positively charged. So when they will pass through the magnetic field, they will bend, they will deflect. So in the electric field, they will be deflected. In the magnetic field, they will be deflected. So what is the choice? Hello?
Yes, sir.
The choice will be A.
Yes, sir.
In the electric field, it is deflected. In the magnetic field, it is deflected. Question number 23. Which row is correct for nuclear fission and for nuclear fusion? In the nuclear fission, we break the nucleus. A larger nucleus is broken down into two smaller nuclei. In the fusion, smaller nuclei fuse together and make a larger nucleus. And this is happening on the stars, this is happening on the sun. This is the energy source of the stars and the sun. So fission, it produces smaller nuclei, and fusion, it is the energy source of a star. So the choice is C. Choice is C. Do you understand?
Yes, sir.
Okay. Which graph shows how count rate of a radioactive isotopes varies with the time? As the time passes by, the count rate gradually decreases, but the rate of decrease is not constant. So the line, the graph should come downward, but it should not be a straight line. It should be a curve. So A is the best choice. Do you understand this question?
Yes, sir.
Okay. For which purpose is the radioactive isotope carbon 14 used? It is used for carbon dating to find out the age of ancient bones. Yes, it's used for carbon dating. So what is the choice?
Dating of ancient bones. A.
Yeah. Question number 26. When dealing with radioactive materials, there are possible dangers. Which statement is correct? Beta particles can pass through skin and damage body cells. That is true. Materials that emit only alpha particle must be kept in thick lead containers. To some extent, that is right. But other radiations given out, that even then they should be kept in the lead container. Beta can be stopped even by a paper wrapper. Radioactive materials are safe to handle after 2 half-life. That's not true. These sources of gamma radiation are dangerous because they have long half-life. That is totally wrong. Gamma radiation, we don't know the half-lives are long or not, who are giving out gamma radiation. A is the best wording. A beta particle can pass through skin and damage body cells. So A is the best answer. Understand?
Yes, sir.
An isotope X is radioactive and has a half-life of 4 years. A sample initially contains 8,000 atoms of X. After how many years will the sample contain 1,000 atoms of X? So half-life is 4 years. So from 8,000, it should come down to 1,000. So let's see. Let's see. Initially, the reading is how much? 8,000. When the 1/2 life will pass, the new reading will be how much? 4,000. When another half-life will pass, the reading will become how much? 2,000. When another half-life will pass, the reading will become
1000.
1,000. Okay. So let's check how many half-lives have passed. 1 half-life, 2 half-life, 3 half-life. Okay. So the time will be equals to 3 half-lives, and each half-life is of 4 years. So we multiply them. So the time passed by is 12
12.
years. Okay. So the total time passed by, because the 3 half-lives have passed, 3 multiply 4. Each half-life is 4 years. So 12 years. So what is the choice here?
C.
C is the right answer. Okay. What is the safest way to dispose of a large quantity of highly radioactive waste? Burning it on a fire? No. Burning can do no damage. Burying it in dry rocks deep underground, that is true. Pouring it down the drain, no, that's wrong. Pumping it into a river, that's totally wrong. So B is the right. This is the way to we make tunnels in the rocks and we bury the radioactive material there. So B is the right answer.
Okay, sir.
The count rate from a radioactive material falls from 4,000 counts per second to 50 counts per second in 12 minutes. What is the half-life? You see, 4,000. So it will reduce 4,000 to 50. It was, I think, not 4,000. It was 400. Huh? It was what? What is the number given? 400 to 50. Let's see how many half-life. So the reading is, first of all, the reading is how much? 400.
400.
When one half-life will pass by, the reading will
200.
become how much? 200. When another half-life will pass by, the reading will become
100.
100. And when another half-life will pass by, the reading will become how much?
50.
50. It will become 50. Okay. So let's see how many half-lives have passed. This is one half-life. This is second half-life. And this is third half-life. So basically there are three half-lives passed. And this happened in 12 minutes. This happened in 12 minutes. So the whole procedure happened in 12 minutes, and we know that there are three half-lives involved. So 12 divided by 3, and the half-life is 4 minutes.
4.
Because in 12 minutes there are three half-lives passed. So 12 divided by 3 and 4 minutes. So the half-life is 4 minutes basically. So the best choice is D. Okay. Question number 30. A nuclei, one hydrogen nuclei, two to form helium nuclei, releasing energy. Which word correctly complete gap 1 and 2? Okay. In nuclear fusion, this happened in nuclear fusion, which is happening on the sun and the stars. In the nuclear fusion, hydrogen nuclei join together to form a helium nuclei. This is happening on the sun. This is fusion. So what is the choice?
C.
C is the right choice. Okay. So this is a long worksheet, and my lesson is over. And today we are able to do 30 questions, 30 MCQs of this worksheet. I will try to make another video, and I will complete that worksheet in that video. But in this video and this lecture, we are only able to do 30 MCQs of this worksheet. This was a worksheet related with the radioactivity, and I can tell you that I have taken this worksheet from a website. The name of the website is savemyexam.co.uk. So my name is Ferhan Mazher. Today is 20th November 2020. I was with the 11 Cambridge class, and we were working on the radioactivity. The subject we were studying was Physics 5054. So, dear students, that's it for today. So everyone, today there was only one student with me, Saida Muskan Fatma. So thank you very much, and have a good day.